So in the last video, we talked about search trees and binary search trees, and that it would be good if they would be balanced, because that would make sure the time complexity of the basic operations is O log n. So what we wanted was that we had a balance condition in our search trees that ensures the depth is O log n, and also that can be maintained in O log n time for each put and remove, so that the overall complexity of our methods stays O log n. And I wanted you to think a bit about how to ensure this. So one way we can do this is with AVL-trees. So they are called this way because they're invented by Adelson, Velsky, and Landis. So what are AVL-trees? So AVL-trees are basically binary search trees with the following balance condition. The heights of the children of each node differ by at most 1. So in this example, this is a valid AVL tree because for each node, the heights of the children differs by at most 1. So we see for this node, it has a child with a height of 2 and a child with a height of 3 that differs by at most 1. And this node has a child with a height of 2 and 1, also differs by at most 1, and 2, 1 and 1 that differs by 0. So it's also at most 1. So all nodes in this tree have childs that differ height at most 1. And for example, here's an invalid AVL tree, and what we see here is that this node has 2 children, one with a height of 3, one with a height of 1, and the difference is more than 1. So this node makes this AVL tree invalid. And actually, if we look at the root node, it also has 2 childs, one with a height of 4 and one with a height of 2. So this node also makes the tree invalid. So with this balance condition, the get method of the tree is actually quite simple, because the only thing we need to do is search for it, and we can just do that with the method we saw in the binary search tree and update it. And there will be no difference in structure of the tree. So that means we don't have to worry about that a valid AVL tree becomes an invalid AVL tree. This is different for the put and the remove operations because they might change the structure of the tree. So if we put a key value pair somewhere where the key already exists, we can just update the key. So that's also easy. But if we have a new key, then we make a new node, and that might change the tree. So let's look at an example where this happens. So say we have this tree and we want to insert 50. What we do is we just use ordinary binary tree insertion. So we look at 30, 50 is higher, so we go to the right subtree. We look at 80, 50 is lower, so we go here. 50 is lower again, so we go here. And then we're here. And then we see that 50 is higher than 40, so we create a new node here. And now we've updated the height of all these 4 nodes. The rest of the nodes, the height is not updated, so we don't have to look at those nodes to see if we still have an invalid AVL tree. So we go from here and then up the tree to see if we still have a valid AVL tree. So let's look. 50 is of course balanced because it has 2 childs of height 0. 40 is balanced because this is height 1, height 0. 60 is balanced because this is height 2 and height 1. 80 has height 3 and height 1. So this is an unbalanced node. So what we're going to do here is we're going to try to repair this. We're going to change the structure in this part of the tree to make sure this is balanced again. So how we're going to do this is we're going to change the position of these nodes. We're going to do this like this. So what we basically do is rotate it to the right here. So the 60 goes here, the 80 goes to the right, and the 40 goes a bit up. And you see that it's still a binary search tree because this subtree is still lower than 60 and this is higher than 60. But we changed the structure, and now the heights of the childs of this node are 2 and 2, and here they are all balanced. So this looked a bit like magic, how we restructure this. So let's have a look at these restructurings. So the building block of such a restructuring is a rotation. So here you see a single rotation. And what happens here is that we change basically the order of x and y. So y is here the highest in the tree, and we want to replace this by x. So what we do is we put x here. Then of course y is higher than x because x is in the left subtree of y. So x has to be lower than y. So y is higher than x. So y should now be in the right subtree of x. So it has to go here. And the subtree T1, which contains of a lot of other nodes here, was lower than x. So it stays the left child of x. T3 was higher than y, or at least the first node in this subtree T3. So this stays the right child of y. And subtree T2, or at least the first node of this subtree, is higher than x because it's in the right subtree of x, and lower than y because it's in the left subtree of y. So that means we put it here because then it's in the right subtree of x still, and still in the left subtree of y. So we can just do this, and we still have our condition where the subtrees of the nodes where the left subtree is always lower and the right subtree is always higher. We change the structure of this tree. Now, using this rotation, we can do two tri-node restructurings, or two different ones, and then also the ones that are the mirrored versions of those. So for the first one, this is basically the rotation applied to a bit more nodes, you see here. So what we basically do is we change these y and z. So the y moves up, and that means the z moves here. And x, which was basically the first subtree of y, is now still the first subtree of y. The T4 was the right child of z, so it stays there. And the T3 is the one that changes from the right child of y to the left child of z. So you see here that when all these trees had the same height, then of course this is unbalanced because y has then the height of T2 plus 2, and if this is the same height, then it differs by 2, and here you see that it's balanced again. The other restructuring we might need is this one, and I hope you can figure out to puzzle out for yourself a bit how two rotations we saw earlier can lead from this changing to this. So these are the two restructurings that we might need to do when we insert elements into this tree. So let's look at an example of that, and let's this time remove an element. So let's remove 13 in this tree. So since 13 has 2 childs which are null, we can simply remove it. So we just do this with ordinary binary search. So we look at 30, 13 is lower than 30, so we go here. It's higher than 12, so we go here. We find it, and then we remove it. Now we go up, and each time check whether the heights of the subtrees are the same. So immediately with the 12, we already see that this subtree has a height of 2, and this subtree has a height of 0. So we're gonna need this tri-node restructuring to fix this. So I hope you can already see what we're going to do. We see that the left part of this 12 is higher than the right part. So we're gonna need to restructure this by rotating it to the right. So what's gonna happen is that this 6 is gonna move up. This 12 is then gonna move down to the right because it's higher than 6. This 4 remains the left child of 6. And the 7 was the right child of 6 and the left child of 12. But now it will be the left child of 12, which will then be the right child of 6. So it's going to be like this. And now we can again look at the heights here. With this node it's 1 and 0. With this node it's 1 and 2. And with this node, it's 3 and 3. So these all have the correct heights. Now let's remove 12, for example. So in this case, we see that 12 has 2 childs which are not null. So like we saw in the last video, what we're going to do is we're going to replace the 12 by the highest node in the left subtree. So this is going to be 7. So let's replace it there, and then again check for the heights. So in this case, we have a height of 1 and 0, we have a height of 2 and 1, and we have a height of 3 and 3. And these are all balanced, so there's no need to restructure. So here you saw the operations of an AVL tree and why they stay balanced. Now let's look at the time complexity. So what we again saw was that tri-node restructurings take one time because we do it with a certain amount of nodes. The get, put, or remove, they visit downwards, like the binary tree search, and we visit h nodes, where h is the height of the tree. And then when we move up, we again do h comparisons to check whether the tree is still balanced, and at most h tri-node restructurings. So as long as h is the height of the AVL tree is O log n, we're good. We just have methods that take O log n time. Question is, does this balance condition of the AVL tree guarantee that our height is O log n?